think it's going to work. So this is Dr. Jones with ANP2, lecture test 2, video 3. Yay! Okay, so hopefully that last video recorded and with audio. Ooh, wrong way. Okay, so that gives us top of page 9. We already did the bits with pages 4, 5, and 6. So we're at catecholamines and peptide hormones are not lipid soluble and bind to extracellular receptors. Let me write down video 3, Noteset page 9. Oh, ooh, and the timer. My busted up screen. 20 minutes. So that it won't take 3 hours to load on YouTube. Fingers crossed. Okay, so the hormone is the first messenger. We need our pen back. And I want the blue. I liked the blue on the blue. Red felt a little neon. First messenger. Hormone is the first messenger. The hormone binds to the hormone receptor and activates the second messenger. The second messenger, some of the second messengers are cyclic AMP, cyclic GMP, and calcium. Amplification is when a few hormone molecules can make more than 1,000 second messengers, so it magnifies the effect, it amplifies. Receptor cascade is when a hormone starts a sequence of reactions, and then the cell reacts in many different ways all at the same time because of the receptor cascade. The link between the first and second messengers, G protein activated, G protein activated, G protein activated. So whether it's cyclic AMP, still cyclic AMP, calcium, G protein. Hormone binds to its membrane receptor, which activates a G protein. Cell's response depends on the nature of the G protein and its effects on the second messenger. Next slide. Oh, back to page 4. So we filled in the eicosanoid bit already. Remember, we don't need those terms. But we did not talk about the steroid hormones because they're more interesting. So let's do that now. Yeah, we're on page 6. Okay. Steroid hormones and how they work. So they have intracellular receptors in the cytoplasm and in the nucleus. They are, of course, lipid soluble, meaning they diffuse across the plasma membrane. I'm going to keep going because you can pause and write all that down real quick. How? Well, it activates or deactivates genes. Remember, if there's a receptor in the nucleus, is going to do something about altering gene expression. So activating and deactivating genes, definition of altering gene expression. And that changes the rate of DNA transcription. DNA is the same thing. Altering the rate of DNA transcription is activating or deactivating genes. It's the same thing, which changes the pattern of enzymes and structural protein synthesis. So enzymes are proteins, and structural proteins will be like the structural proteins we had in the muscle cells, like actin and myosin, and can change the metabolic activity. That will be the enzymes, and the structure. That'll be the structural proteins. So this kind of all says the same things, although when we get to the thyroid, we'll see that it can play out in slightly different ways. Oh, I did want to say the receptors in the cytoplasm are storage. So this is the steroid hormones where they're bound hormones. So you've got a couple weeks supply in the bloodstream, and then you have backup storage in the cell. Maybe this is the main storage and the bloodstream is a backup storage. Pantry items. Okay, so the thyroid hormones are not lipid soluble. They are transported across the plasma membrane. After all the sections on how to transport things across the plasma membrane, our book has a surprising lack of detail here. Oh, it's transported across the plasma membrane. Every other thing that is transported across the plasma membrane, there's like a paragraph describing exactly how. And here we're like, transported across the plasma membrane. I think we can run with it though. So here we have intracellular receptors in the nucleus and on the mitochondria. What do mitochondria do? Okay, I know you just said make ATP. I'm just teasing. I think I've been sitting here staring at this computer for far too long. That happens. So what the mitochondria makes ATP, and what do thyroid hormones do? T3 and T4. Thyroid hormones are energy. Next column, same page. Okay, behind there, and these thyroid hormones, by the way, are on page 4. So behind here we have activates genes, changes the rate of enzyme transcription. So the thyroid, excuse me, only changes the rate of enzyme transcription, not also the structural protein transcription like the steroid hormones do. Or it increases ATP production if it lands on the mitochondria, enzyme transcription if it lands on the nucleus. Okay, back to page 9. Excellent. Let's talk about steroid hormones. If I can turn the page. That's not what I wanted to talk about. Still not what I want to talk about. Okay. Steroid hormones are lipid soluble and therefore can diffuse across the cell membrane. Steroid hormones bind receptors in the cytoplasm or nucleus. This is all stuff we've said before, but we're getting it in the note set, this part of the note set this time. Hormone receptor complex then activates or deactivates specific genes with a G, altering the cell's rate of DNA transcription. This affects both metabolic activity and the structure of the target cell. Thyroid hormones enter via an unnamed transport mechanism and binds to receptors on the nucleus or the mitochondria. Hormone receptor complex in the nucleus activates specific genes with a G, or changes the rate of DNA transcription, which affects metabolic activity by making more or less enzyme. And then thyroid hormones bound to mitochondria make the mitochondria make more ATP. How are we on time? Oh, I got like 12 minutes left. It's the first time I've done this lecture this semester, so I didn't know how long it would take. So we're going to work on a second note set page in the same video. Okay, endocrine reflexes and their triggers. Bullet, bullet, bullet. Humoral stimuli, hormonal stimuli, and neural stimuli. So the humors are your fluids. So these are changes in extracellular fluids. We'll talk about when blood sugar goes up, when blood sugar goes down, when blood calcium levels go up, when blood calcium levels go down. So the humoral stimuli are the amounts of things in the fluids, which is most often the bloodstream. Hormonal stimuli is the absence or presence of the specific hormone. And we'll talk about these, especially with the complex endocrine reflexes. We'll talk about this quite a few times. Things like thyrotropin releasing hormone, this will be our main example here. Thyrotropin releasing hormone from the hypothalamus causes the anterior pituitary gland to make and release thyroid stimulating hormone. And then thyroid stimulating hormone makes your thyroid gland make and release that's a 3, T3, and that's an ampersand, T4, that's a capital T. I did try with the trackpad, and that was not better. Neural stimuli. These are neurotransmitters at neuroglandular junctions. So the neural stimuli will cause the release of, I messed that up, epinephrine and norepinephrine, which is caused by synaptic activity at the neuroglandular junction in the adrenal medulla. A simple endocrine reflex is one hormone. I have got to stop writing these things because it takes forever. Okay, one hormone and negative, and here's your basic reflex arc from last semester. Negative feedback, effectively, if something is too low, you release the hormone that raises it, and if something is too high, you release the hormone that lowers it. Slow blink. Okay. Let's talk about the pituitary gland. Pituitary gland is called the hypophysis, and in fact, this little bone where it sits, this little indentation, is called the hypophyseal fossa. It all comes together. Two parts to the hypophysis, the pituitary gland, the adenohypophysis and the neurohypophysis. The adenohypophysis is the darker red anterior pituitary gland, and I tend to write it as the ant pit, which you do not say in front of anyone else. And then the neurohypophysis I tend to call the post pit. So if I say those are not approved terms. This is just me not liking writing out the entire word. It's faster when you're taking notes. So the pituitary gland releases, okay, wasn't what I was expecting, but we'll go with it. 9 peptide hormones, 7 from the anterior lobe, the adenohypophysis, and 2 from the posterior lobe, the neurohypophysis. The hypothalamus has both endocrine and neural tissue. And it is, I will say that in a minute. And the hypophysis is the pituitary gland. Highest level of endocrine control is provided by the hypothalamus, which works in 3 ways. 1, it makes ADH and OXT and releases them from the posterior pituitary gland. Number 2, it secretes regulatory hormones, and these will be releasing hormones and inhibiting hormones. And then they go through the bloodstream to the adenohypophysis, the ant pit, the anterior pituitary gland. And 3, direct neural control of the adrenal medulla at neuroglandular junctions, causing the release of epinephrine and norepinephrine from the adrenal medulla. Neuroendocrine responses are complex endocrine reflexes that involve the hypothalamus. They are the antithesis, the opposite of a simple endocrine reflex, which is just one hormone. Anything that involves this hypothalamus here is complex. So extra. Explain how the hypothalamus can vary its messages. Okay, this is cool. it changes the amount of, I should have underlined amount, the amount of hormone secreted, and that can change the message. It can also change the frequency of hormone release, which is how often, and it can release hormones in patterns. And different patterns, different frequencies, different amounts together give quite a variation of different messages that can be given with just a few hormones. So it's pretty interesting. That was page 10. Turn on the timer. Oh, I got like 5 minutes left. Okay, babies. So remember, purple was your neuro stuff and blue was your epithelial stuff. So the pituitary gland is both. So the neural part makes the neurohypophysis, which is axons from the hypothalamus that release the ADH and OXT, whereas the adenohypophysis is our traditional epithelial gland made of epithelium, and that will release the peptide hormones. And there's a whole list of those, and we will fill in charts here in a minute, or next video. Probably next video we'll start that. We'll finish page 11 on this video because the top of page 12 starts a whole new thing. So we'll finish page 11 for this video and then change certs and make another video. That's the plan. So the anterior lobe of the adenohypophysis has 3 parts. Pars. So the pars distalis is the main part. It makes 6 hormones. I was trying to circle it and then I was trying to say 6, and so it came out a weird 6. The pars intermedia makes, okay, I was gonna like draw a line to it, but it makes 1 hormone, so yeah, that got awkward. And then the pars tuberalis is part of the infundibulum. I'm recording. Okay, so why would you expect endocrine organs to be highly vascular? Well, endocrine organs release hormones into the bloodstream, so you would expect to have lots of blood vessels for lots of bloodstream for the hormones to be released into, like the picture shows. Excellent. Okay, so the hypothalamus is the boss of the endocrine system and tells the pituitary gland what to do, while the pituitary gland is a manager telling many other endocrines what to do. True or false? True. So in the note sets, when I came across a statement that I couldn't figure out how to make a question, I just threw true or false at the end of it. So if it's in the note set and it says true, false at the end, it's true. The lecture test could go either way. Note set's all true though. So the hypothalamus releases specific regulating hormones that go to the anterior pituitary gland, the adenohypophysis, specifically the pars distalis, but we'll talk about that. Fenestrated capillaries are permeable. They have holes in them. They have pores in the walls. So capillaries are such small blood vessels that it's a single simple squamous epithelium thick. The wall is a single simple squamous epithelium. And these have holes in them, or pores, and that allows the hormones in and out of the bloodstream more quickly. 2, portal vessels. Okay, next, portal vessels. Okay, whiteboard. We need a whiteboard. We're going to cover this. It was up W. Ha. Okay, so let's draw a heart. I can't draw. Best heart I've ever drawn. I'm so impressed. That is awesome. Okay, so what happens is you have red oxygenated blood from the left side of the heart that goes out to the body. There you go. And what happens in the body to the oxygenated tissues? Do we seriously not have purple? Okay, we're using hot pink, but it means purple because red and blue makes purple. So in the tissues, you have capillary beds. Capillaries are the very smallest of the blood vessels. Often they're so small that the red blood cells have to fold in half to get through them. And there are capillary beds all over the body. And in the capillary beds, the oxygen leaves, some of the oxygen leaves the blood to go into the tissues to diffuse to the cells, because the cells need oxygen to make ATP. And then the carbon dioxide will diffuse into the bloodstream. So now we have deoxygenated blood, which we represent with blue. So, and there's our timer. Okay, so the deoxygenated blood from the top third of the body, capillary bed, goes into the heart this way, and from the bottom 2/3 of the body goes into the heart this way. And then the deoxygenated blood goes down and then out. And where does it go to? The lungs. What happens in the lungs? Capillary beds. Capillary beds happen in the lungs, where in the smallest vessels, the carbon dioxide leaves the bloodstream, goes into the air that you exhale, and oxygen from the air you inhale goes into the bloodstream, and now you again have, pen color red, oxygenated blood. And so this oxygenated blood goes into the left side of the heart, goes down, and then out to the body. So our pattern here is, I'm going to do the pattern in just black because it takes a long time. You have the heart, and then a capillary bed, and then the heart, and then a capillary bed, and then the heart. And that's literally what your blood does all day long. Heart, capillary bed, 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 all day long. So that's how that works. Portal systems are the exact same, but completely the opposite. Because in a portal system, now I have to write that down, portal system, where you go heart, capillary bed, heart. And so this vessel right here is your portal vessel. And it could be an artery, it could be a vein. Basically, you slice it and look at it under a microscope to see if it's an artery or vein. So this is the portal system where you break your pattern of heart, capillary bed, heart, capillary bed, heart, capillary bed, heart, capillary, ad infinitum. And here in a portal system, you go from the heart to a capillary bed to a second capillary bed before you go back to the heart. We're going to talk about this portal system here. We're going to talk about another portal system when we get to digestive, because it turns out your digestion is like one giant portal system, but we'll get there. For now, we have a tiny portal system, and this is called the hypophyseal portal system. And it takes the regulating hormones. Remember, we had releasing hormones and inhibiting hormones. And they go from the hypothalamus in this capillary bed through these portal vessels directly into a second capillary bed. In this way, these releasing hormones and inhibiting hormones, regulating hormones together, the regulating hormones go directly to the pars distalis of the anterior pituitary lobe, the adenohypophysis, directly so that they can have immediate effect. Follow all that? If not, rewind it and watch it again. Okay, so the portal vessels, back to the note set, link two capillary networks. The portal system takes blood from one capillary bed to another, and the hypophyseal portal system takes all the hypothalamic regulating hormones directly to the adenohypophysis, which is the anterior pituitary gland. Okay, so let's finish this page. List and describe the two classes of hypothalamic regulatory hormones, releasing hormones and inhibiting hormones, which we have said. Here's how you spell it. The releasing hormones cause the ant pit to make more hormone, and the inhibiting hormones cause the ant pit to make less hormone. So it's that sign for inhibitory. And that sign for, yeah, that got awkward. That got awkward fast. Moving on. So the releasing hormones make the ant pit make more hormone. The inhibiting hormones inhibit. They make the ant pit make less hormone. They inhibit hormone. Okay. Tropic hormones. All of the pars distalis hormones are tropic hormones. So trope means a turning, and these tropic hormones, the anterior pituitary hormones, turn on other hormones. Like we said, that thyroid stimulating hormone causes the thyroid gland to make thyroid hormones. So this used to, the old name for thyroid stimulating hormone is thyrotropin, because it's a tropic hormone, because it turns on the thyroid gland to make thyroid hormones. Negative feedback. Okay, so here we've got prolactin releasing factor. I think it's a hormone now. They figured out what it was made of. And that causes the anterior lobe to make prolactin, whereas the prolactin inhibiting hormone makes the anterior lobe not make prolactin. And prolactin, lactin like lactate, makes milk. So prolactin releasing factor from the hypothalamus makes you make milk. Prolactin inhibiting factor makes you not make milk. All right, so that's negative feedback. Oh, that didn't answer the question. So when you have lots of prolactin, I'm sorry, when you have lots of, when you have lots of prolactin, that, remember the red is increase, that increases the inhibition, whereas it decreases the releasing factor, which is another set of double negatives. So, okay, y'all know the bit where Lucille Ball, because everything goes back to Lucille Ball. I mean, Star Trek. If there were not Lucille Ball, there would not be Star Trek. True story. Okay, so the bit where Lucille Ball has a job at a chocolate factory, and the chocolates are coming through, but the conveyor belt is going faster and faster and faster and faster. And Lucille Ball has no idea what to do with all of these chocolates. She tries eating them, she puts them in her hat, she stuffs them in her bra, she does anything and everything. If only when there was too much chocolate, Lucille Ball could hit the stop button. Like turn on the off button or turn off the on button. Either way would be super handy. So that's the negative feedback. when there's too much of a hormone, you turn off the hormone that makes the hormone make the hormone. You just turn off the whole thing. Just go to the beginning of the factory and shut it down. Negative feedback. Okay. And that was where we're going to quit for this video. So we did pages 9 and 10. No, 9, 10, 11, 9 through 11. Okay. So this has been a video lecture. AMP2 lecture test 2 video 3. Yay, we made it through 3. So thank you as always for tuning in. The education must go on. It's more imperative than ever. Dr. J out. Control, Command, Escape. Got it. Thanks, guys.